Alright, in this lesson, we are going to start working with perpendicular lines. In particular, there are a few facts about perpendicular lines which we would expect you to know. These facts that we are working with will allow us to apply perpendicular lines and combine them with the parallel lines that we were working with before. In particular, we're going to look at a perpendicular bisector and distance. We have already worked before in class where we discussed that the perpendicular bisector, well, what does bisect mean? Bisect means to cut it in half. Perpendicular means they cross at a 90-degree angle. So a perpendicular bisector cuts a segment in half, and it cuts it in half at a 90-degree angle. Quite simply, if we had a picture where we had a segment, we know that this would be perpendicular because we wind up having that 90-degree angle. We know that, oh, okay, those got linked together. We know that if we're looking at the middle or a midpoint, this slanted line would be a bisector because it cuts the segment in half. If we do both, cut it in half, add a 90, that's a perpendicular bisector. And of course, one of the reasons that we care so much about bisectors, or the reason that we care so much about perpendicular, the distance from any point is straight at it. If you're going to say, for instance, just from me to you, Ryan, how far away am I from you? Well, the distance that we would talk about is in a straight line. If I were to come right at you at a 90-degree angle, that's distance. We wouldn't include the thing where I walk all the way around the desks to get to you. Now, there may be things in the way, but that's fine. You can have a wall in between, and it may not be possible to travel along that path, but it's still the shortest distance. So, just looking at this first example, what's the shortest segment from point A down to the side BC? Shortest segment is distance. Distance is always at a 90. When you look at this piece, that should tell you you are looking for a 90-degree angle. That is, you're looking for perpendicular. And since we've got it right there, how long is that piece? Done. That's all this one was taking. Well, that's going to allow us then to recognize that this piece from A to C, it still goes from point A down to the other line BC, but it's not the shortest possible distance. It's not the shortest way to get there because it's not at a 90-degree angle. Because 12 is the shortest possible one, we could use this to build an equation. In particular, we know that this piece has to be bigger than 12. So we could simply say x subtract 8 has to be bigger than 12. I'm a fan of building my inequality so that the variable is on the left. This isn't the only way to do it. I've had a lot of students in the past would simply like to say 12 is shorter than the other one, and they like to build it based on having less than. It doesn't matter, both of them are correct. You could solve it either way. I just like having my variable on the left because then I don't have to worry about flipping it at the end. You know, that's easier for my brain. Your brain can be different, and you may like to simply think 12 is shorter than the other ones. That's fine, especially because the directions at the top are already talking about things being shorter. Either way, you wind up taking this approach where you add 8 to solve it. And so you get x has to be bigger than 20. And we're done. Now, besides working with shortest distance, there are several other facts that you should know about perpendiculars. And for the moment, I'm going to get rid of, no, I can't fill that in. For the moment, I want to get rid of all the words, because the words are less important than the stuff on the right-hand side. One of our expectations for you are that you would recognize the hypothesis and allow it to bridge over toward the conclusion. You are supposed to see, anytime you see these pictures, you are supposed to recognize that this column on the right, that's the extra piece that you get for free. And in this top one, this is telling us that if we have a linear pair, looking right here, we've got two angles up on the top, 1 and 2. They do form a straight line, so we have a linear pair. But more than that, we can also see in the picture that we have our two tick arcs. So we know that those two angles are also congruent. So if we have a linear pair, and I'll remind you that this upward pointing arrow is the symbol we use in logic for the word and. A linear pair, and they are congruent, then you will get the fact that they are perpendicular. It's essentially allowing us to conclude that when we see this picture, we know that those are 90-degree angles, which should be fairly intuitive, right? If they're the same, and because they're a linear pair, they add up to 180, what number added up twice will give you 180? 90. Because it's a 90, that's what makes it perpendicular. This particular theorem doesn't have a standard name. In some math textbooks, they don't give it a name at all. In some math textbooks, they'll give it one name. In some books, it'll be a different name. For us, if we're not going to use the symbolic logic to reference it, this is the linear pair perpendicular theorem. That's what we'll call it. Of course, we want our names to remind us what the things are about. This is about linear pairs being perpendicular, so that's what we're going to call them. Progressing toward the second one. This one is saying, you'll notice right off the bat that we have the arrows on our lines. This is a problem then that begins with having parallels. If the lines are parallel at the beginning of the problem, okay, so we'll say we have parallels, but we'll also notice we are given this 90. We're given perpendicular. If we have parallel lines and the transversal is perpendicular to one line, what does that cause? Or rather, what would you know is true? The transversal has to be perpendicular to the other line. So basically, it's saying if it crosses the top at a 90-degree angle, we know it's also going to cross the bottom at a 90-degree angle. Which should be fairly intuitive because we know that since they are parallel, and we've got a 90-degree angle, corresponding angles have to be the same. So corresponding angles will be the same. 90 matches 90. That's all that we're doing. We're just using our tools from previous lessons. This one is common enough that it has a fairly standard name. That one is the perpendicular transversal theorem. Again, really clever names, right? We're talking about a transversal being perpendicular to a line, so we call it perpendicular transversal. And the last piece that we should take away, the last new theorem that we'll have, is the converse of the perpendicular transversal theorem. Ultimately, the perpendicular transversal theorem, the one in the middle, started by saying if it's going to cross one of them at 90, then it's going to cross the other one at 92. Or 90 also, perhaps I should say also instead of 2. The converse simply works backward. If your transversal is perpendicular to one line, so if it's crossing the top at 90, and the transversal is perpendicular to the bottom line, so it's also crossing at 90. You notice then that we have congruent corresponding angles. And we know that the converse of the corresponding angles postulate then would guarantee us those lines are parallel. Essentially, this just gives us 3 extra tools that we can now use. If we start encountering 90-degree angles, it will allow us to figure out specific parts for when something will equal 90. And this will also give us another tool for how we can claim something is parallel. It gives us a 5th tool for explaining why things are parallel. But as we noted, this is just a special case of the corresponding angles postulate. It's a special case of the converse of corresponding angles postulate. It's just when we use corresponding angles when the number is 90. Now, how could we use those? Well, let's write up a proof showing that. Here's our problem. Given R is parallel to S. Given angle 1 is congruent to angle 2. Prove to me that line R is perpendicular to the transversal. So what's the idea? Well, what do these things tell us? Just thinking about the plan, R is parallel to S. So we know, we get all of those angle things. We know that corresponding angles are congruent. We know that alternate interior are congruent. We know alternate exterior are congruent. We know same side interior are supplementary. We get all of those tools because we have parallel. Which one of those tools would be helpful? Well, which one of those pairs of angles do we actually have numbered? Do we have numbered corresponding alternate interior, alternate exterior, or same side interior? Yeah, we have angles 2 and 3 are corresponding. And so what we would note then, angle 2 is the same as angle 3. Because of our given, we know that angle 1 is the same as angle 2. And then make an observation here. You see that we have a linear pair where the angles are the same. That's perfectly set up for the linear pair perpendicular theorem. That's where we'll get our perpendicular. We're setting it up to use the top one. And so writing up that idea, what's the first thing that we know? Where do most problems start? With the given. So, what were we given? We're given R is parallel to S. And so what does that parallel give us? Having parallels tells us that corresponding angles are congruent. You'll remember that's called the corresponding angles postulate. Well, our corresponding angles were 2 and 3, so we'll say angle 2 is congruent to angle 3. We had a second piece of given information. What was it? Okay, since angle 1 is congruent to angle 2. At this stage, we need to recognize something from algebra. You need to recognize 1 is the same as 2, then 2 is the same as 3. So when we take across that bridge, 1 is the same as 2, 2 is the same as 3, we can bridge that and recognize angle 1 is congruent to angle 3. What was the name of the property that lets us do that? That is the transitive property of congruence. Well, of course, we remember that there is also a transitive property of equality when we do numbers. Finally, because angle 1 is congruent to angle 3, we can use the linear pair perpendicular theorem. And that will allow us to conclude R is perpendicular to T. Because we have a linear pair, and that linear pair is made up of congruent angles, this bottom theorem tells us that the lines have to be perpendicular. We're done. Okay, practicing another proof. Given angle EHF is congruent to HF angle HFG, which is telling us then, just what the ticked arcs are, these two angles are the same. We are also told FG is perpendicular to GH. That's where we're getting this 90. And we are trying to explain why is it that EH is going to be perpendicular to GH. Admittedly, there's something in this picture that's put in there to try to trip you up. And it's not trying to confuse you. What it's trying to do is make sure that you can look at only the important parts of a picture. When you look at this picture, as weird and as complicated as it is, this top line here in the blue, you'll notice that they didn't really talk about that much at all, because it's really not that important. It's not relevant for us. This is a picture that we could redraw, and when we redraw it, it would probably be easier to understand. In particular, when we look at just this set right here, we have these two angles are the same. What is the effect of that in the yellow going to be? What kind of angles are those? You should recognize those are alternate interior angles. And so we are given alternate interior angles are congruent. Because of the converse of the alternate interior angles theorem, that would guarantee us these lines are parallel. Once we have parallel lines, we can now use the fact that they're parallel on a different transversal. If it's perpendicular to the top line, that would mean then that it's going to be perpendicular to the other problem, to the other line. So here's what we're working through. This whole thing is designed for us to say the underlined part in yellow is going to cause lines to be parallel. And then after you get parallel, having a perpendicular transversal is going to make it perpendicular to the other line too. So we need to write up those details now. We have our statements. We have our reasons. And we're starting off with angle EHF is congruent to angle HFG because that was given to us. Recognizing that those were the alternate interior angles, we're using the converse of the alternate interior angles theorem. And that tells us then that the two lines were parallel. Those two lines are EH and FG. Now that we have parallel lines, we'll introduce the second piece of given information. FG is perpendicular to GH, noting that GH is acting as the transversal. And so now we're going to use the perpendicular transversal theorem. If your transversal is perpendicular to one line, then we know it's perpendicular to the other. That gives us EH, the other line, is perpendicular to the transversal also. And we're done. Fortunately, our last example type are simpler than that, but we do get to see how this stuff is used in action and where it actually shows up kind of in the real world, if you will. Like carpentry. If you're using a carpenter square, it's used for drawing a 90-degree angle. You put down a carpenter square along a piece of board, and it creates a 90-degree angle. Slide that over and draw another 90-degree angle. And after you've started these drawings for each one, you can extend it all the way across the board like that. And the whole purpose for drawing those is it then guarantees that these two pieces are going to maintain the good 90-degree corner from the original board. That is, it guarantees that they're actually 90-degree angles, that those two pieces are still going to be parallel to each other. You don't wind up with some slanted, crooked board after you cut it. Why? Why are the lines parallel? all this is asking, which one of our 5 parallel tools can we use? Do we have corresponding angles congruent? Do we have alternate interior? Do we have alternate exterior? Do we have same side interior? Do we have supplementary? Do we have a set of perpendiculars? Well, of course, given that we're working in the perpendicular lines section, that should be a flag that gives you a huge hint that, by the way, you should probably be working with the perpendicular lines. This one is the converse of the perpendicular transversals theorem. We're done. Remember, the converse of the perpendicular transversals theorem says if you begin with a pair of 90s, then you get for free those lines actually are parallel. That's exactly what we were trying to do here. Similarly, why is it that if we have a rip current, why would the rip current have to be perpendicular? Why should the swimmer swim parallel to the shoreline? It's the same reason. They should swim parallel so that they can take advantage of the converse of the perpendicular parallel theorem.